Hello everyone, my name is Jason Kim. The topic my partners and I will be discussing today is grid-tied photovoltaic power generation system. Grid-tied photovoltaic power generation systems are systems designed to operate in parallel with the interconnected electric utility grid. I'm going to talk about various materials used in solar cells. Tony and Lynn will be talking about the operation of inverters, and Ziton will be talking about the advantages and disadvantages of photovoltaic power generation. Solar cells are objects made up of semiconductor material, which applies the concept of photovoltaic effect to convert sunlight into electricity. Photovoltaic effect is a phenomenon which occurs when the photons containing solar irradiation collide with the solar panel made up of semiconductor materials. During the collision between the photons and the solar panel, some photons are absorbed by the semiconductor materials, and the electrons in the sunlight are detached from their atoms, generating direct current electricity. The types of materials used for fabrication of solar cells can be classified into two categories: silicon-based and thin film. Silicon is one of the most popular materials used in solar cell technology. The market share of silicon-based solar cells today is about 80 to 90%. Silicon-based solar cells can be further divided into monocrystalline silicon, multicrystalline silicon, string-ribbon, and amorphous silicon. Monocrystalline silicon is produced using Swarovski process. The typical efficiency of solar cells based on monocrystalline silicon is approximately 20%. The lowest retail price of such solar cells is $1.84 per watt as of March 2011. The typical life expectancy of the solar cells made up of single crystalline silicon cells are approximately 25 years. Multicrystalline silicon is fabricated from blocks of molten silicon carefully cooled and solidified. Multicrystalline silicon is composed of several crystal structures separated by grain boundaries. The presence of grain boundaries results in lower material quality, which ultimately lowers the efficiency of energy conversion. The typical efficiency of multicrystalline based solar cells is slightly less than 20%. The solar cell developed by JA Solar Holdings Corporation, released in February 2011, possesses an efficiency of 18.2%. The lowest retail price of a multicrystalline silicon-based solar modules is $1.74 per watt. Ribbon silicon is a type of multicrystalline silicon formed by drawing flat thin films from molten silicon. This method does not require sewing from ingots and therefore reduces silicon waste, which ultimately results in lower production cost. However, the efficiency of solar cells made up of ribbon silicon is relatively lower compared to the multicrystalline based solar cells. The typical efficiency of string ribbon solar cells ranges between 13 and 14%. However, there have been several efforts to improve the efficiency of string ribbon solar cells. Researchers in Georgia Institute of Technology were able to fabricate a solar cell on string ribbon silicon wafers with efficiencies of 17.8%. In an amorphous silicon solar cell, a thin layer of silicon is placed directly onto a sheet of stainless steel. The thickness of an amorphous solar cell can be 100 times less than that of its crystalline counterpart, as it absorbs light more efficiently. In the past, the efficiency of solar cell ranged between 8 to 10%. Thin film solar cells have become a popular alternative to silicon-based photovoltaic cells due to its attributes such as its flexibility, reduced cost, and lightweight. The market share of thin film solar cells currently ranges between 10 to 20%. Thin film solar cells are constructed by stacking one or more layers of photovoltaic materials on a substrate. There are several types of materials used in thin film photovoltaic technology: cadmium telluride, gallium arsenide multijunction, and copper indium gallium selenide. Generally, the efficiency of thin film solar cells are lower than that of silicon-based solar cells, but their production cost is significantly lower than silicon-based solar cells. Recently, cadmium telluride has emerged as popular choice for producing high volume and low cost solar modules. Its bandgap is almost perfectly matched to the distribution of photons in the solar spectrum in terms of optimal conversion to electricity. The manufacturing cost of cadmium telluride is 76 cents per watt. The total capital cost is 90 cents per watt. The efficiency of cadmium telluride is about 11%. One thing to note is that cadmium is considered an extremely toxic material. However, the exposure of cadmium is nearly impossible as the glass plates surrounding cadmium telluride remain sealed. Moreover, there has been further effort by manufacturers to mitigate the hazards associated with cadmium, which resulted in establishing a recycling program. Gallium arsenide multi-junction solar cells are made up of multiple p-n junctions connected in series. This type of solar cells permits more coverage of light spectrum. The efficiency of gallium arsenide is nearly 40%, which is significantly higher than the efficiency of any material used in solar cell technology. However, the manufacturing cost is extremely high. Therefore, gallium arsenide technology is not commonly used for commercial purposes. CIGS is tetrahedrally bonded semiconductor composed of copper, indium, gallium, and selenium. It is a solid solution of copper indium selenide and copper gallium selenide. The efficiency of CIGS solar cells is the highest out of all thin film-based solar cells, at around 20%. While the production of CIGS is cost less compared to the silicon-based solar cells, the typical conversion efficiency of CIGS solar cells is lower than that of silicon-based solar cells. Traditionally, CIGS cells are fabricated using vacuum processes, including co-evaporation and sputtering. Recently, some non-vacuum processes were developed, which may result in lower production costs in the near future after commercialization of such technology. Now, Tony will be talking about several types of inverters used in solar power generation systems.
I will talk about different inverters being used in photovoltaic applications. The first inverter I will be talking about is the centralized inverter. The configuration is really simple. All the strings are made up of PV modules connected in series, then strings are joined together in parallel connection. The main advantage of centralized inverter is the low installing and maintenance cost, mainly due to the simple configuration. On the other hand, the centralized inverter experiences the string theory problem. Since all the PV modules are connected in series, the current across each PV modules is identical. If one or more modules are covered in shade, the current generated will decrease. Then there will be two scenarios. Either the shaded module pulls down the unshaded ones into a lower current level, or the unshaded module tries to drive the shaded module into a higher current level. Either case, the output power is limited. In order to lower the shading effect, less cells are connected in a string and more strings are connected in parallel. However, since there are less modules in a string, the output voltage is relatively low. It also requires more wire to connect the modules. For the high voltage configuration, more modules are connected as a string. It has a higher output voltage, but it is also more vulnerable to shades. The third configuration is the master-slave configuration. At low irradiance range, only the master inverter is operating. As the irradiance increases, the slave inverter kicks in. The configuration has a higher efficiency, particularly in the low irradiance range. String inverter connects one inverter at the end of each PV string. By doing that, it is possible to optimize each string and increase the efficiency. It also reduces the system wiring. On the other hand, string inverters still face a series shading problem. Other disadvantages include high input voltage requirement and PV modules have to have the same orientation. The AC modules connects an inverter to every single PV cell. It is the smallest grid-tied PV system. Each module can be configured and optimized individually. Ideally, each AC module can adjust itself to maximize output. Therefore, the system does not face series string problems and has a higher efficiency. Other advantages include easy to extend or deduct system and easy to replace modules. The main disadvantage is the relatively high cost since PV panels require an inverter.
Hi, my name is Zitong Zhang. I will be talking about the grid-tied PV system. And I will be discussing its advantages, challenges, as well as the economic impact. Here are the advantages. It is clean and quiet, since it does not have any greenhouse gas effects. It is also very mobile. You could assemble, install, and reassemble at almost any location. However, it has to be in the city or near the grid. The grid is the main energy supply network of the country. Since the grid-type PV system does not have a battery. In addition, it does not need to have maintenance because all solar panels have a really long lifetime, approximately 20 years. It varies in size depending on the specification of the power desired and voltage desired. Here are some challenges. It is very toxic byproduct while the solar panels were being made, and it is really hard to get rid of them. It is also more expensive to produce than other alternative energies. It is also at times unreliable when rainy and cloudy days strikes. You can have a significant efficiency decrease, and most obviously it does not work at night since there are no sunlight. In the world we live in, where human population continue to grow and global economic expansion and the demand of electricity will significantly overshoot. It is predicted that in 2006 we have 18 trillion kilowatts per hour, gradually increase to